So here's what I need to do. I need to take the integral.
Is it two of them? Like the area of the red one minus the area
Of the other one, yes. I'm going to do two separate integrals. So the first one, they both have the same limits of integration. They both go from pi over 6 to 5 pi over 6. But the first one is 1/2 3 sine theta squared d theta, right? Minus the other integral, pi over 6. You could combine these into a single integral.
Oh, yeah.
Okay, we could. I'm trying to get you to understand the idea that we're getting two areas and subtracting them. And the other one would be 1/2 and then 1 plus sine theta squared d theta.
Because this is just like the, when we were finding the two functions, you just subtract
Yep.
the area between.
Area between. And that's it. Now, I believe, if I'm not mistaken, I pulled this example from the book. I believe when you get to this integral, that it can't be done easily. Hold on, let me see. Oh, no, I'm thinking arc length. I'm thinking the arc length one. Never mind. Yeah, so this one we could work out, right? Do I need to? Because we're already at 10 o'clock, so we're okay? You understand what you would need to do with this? Okay. Last thing, arc length of a polar curve. So there's a formula for arc length. We will not derive the formula, but that's what it is. If you have a polar curve restricted on an interval AB, the length of that curve is the integral from A to B of square root of r squared plus dr d theta. That's supposed to say dr d theta, not dr r theta. Typo. And then d theta. Squared and then d theta. So let's just set this one up. Find the length of this cardioid right here. Find its length. So if you were to start drawing this, draw the whole thing, take it off the piece of paper, stretch it out, how long is it? So do you remember what the angle was that drew the cardioid? Was it 0 to pi? Do you remember?
It was sine, or 1 plus sine theta.
No, I'm saying, did we draw the whole thing in pi or was it 2 pi? It was 2 pi. Okay, so our integral here, we want it to go from 0 to pi. The length of this will be the integral from 0 to 2 pi. Square root of, now just follow the formula. R squared, right? Which would be 1 plus sine theta squared plus dr d theta squared. So cosine theta, then squared. And then that's it, right? D theta. And this is going to be problematic. This is what I was saying. This example is done in the book, but when they get to this point right here, they say you can use like a computer algebra system to do this integral. So I would never give you an integral that you can't actually do. No, because you would get a square root of like 1 plus sine or something. Yeah. Power series would even be tough too, because even though you'd be able to convert the inside to a power series, you would have the square root of the power series, which would be, that's something we hadn't really messed with.
If you used half angle or power reducing to turn the cosine into sine.
You'll still have, look, I'm telling you, it doesn't go easy. Yeah, it doesn't go easy.
Theorem, and then the inside will become 2 plus 2 pi or 2 sine theta.
Huh?
But you can't square root that.
You can't square root it. That's the problem. Yeah. Okay, so the idea is just that you see how it's set up. You have to pay attention to the limits of integration. Make sure you plug r in, take the derivative, square it. Now, in the homework assignment that I gave for this, which I told you I'm going to do after class, these polar curves are all doable. Like, I'm going to be able to get to an answer. I'm going to be able to integrate them. So I highly recommend that you watch those videos, because if on the final you get one of these and you're like, well, I never even saw anyone take one all the way through, like, that might hurt. All right, we good?
You know, there's going to be one of those.
That's it. We are done with Cal 2. I'm going to stop the video. We don't really need this on video.